Okay, so we're very glad to have Mark Kamsma from the University of East Anglia here today, who will be talking about independence relations in AECs. So you can start when you're ready, Mark.
Thank you, John. Thank you for inviting me as well. So yeah, this is about independence relations in, well, actually abstract elementary categories, which, as I will explain, will be slightly different from AECs. And this is really inspired by the work by Mike, Hirschi, and Sebastian, which I think have been talked about in the seminar already. So I'll mention that a few more times. So yeah, this is really a way of doing model theory in a category theoretic setting. And my keyboard work? Yeah, there we go. So I'll first explain a bit about this kind of model theory that we will be doing, which we call classification theory. And then I'll introduce this framework that I call abstract elementary categories, or AECATs. And then finally, this comes together in the last section when we consider what these independence relations. And I'll explain how these are related to this classification theory. So let's start with this classification theory. It was kind of started by Schilach around 1970, and the idea is to classify first order theories based on how complicated the behavior of their definable sets is. So the most well-known class of this classification theory is what we call stable theories. Probably maybe you already heard that name. And some examples of stable theories would be our vector spaces or algebraically closed fields. So these are very well-behaved structures in that sense. For example, in our vector spaces, the definable sets are really easy to understand. They're either finite sets of points or translates of linear subspaces or Boolean combinations of those things. And there's this really nice picture from the website forkingdividing.com by Gabriel Conant. And this is really a picture of this classification theory, if you will. So these different areas are the different classifications that we can give. And these red dots are the theories. So for example, this is the class of stable theories, and all these red dots in here are stable theories. And I want to focus on kind of a specific part of this picture in this talk, namely that of stable, simple, and NSOP1. So simple is over here, which is, as you can see, more general than stable. And there are definitely things that are simple but not stable. But it's still pretty well behaved. And then this is this NSOP1, which is again more general than simple. So this is nice kind of hierarchy of classifications. And there are many more, of course, interesting classifications, as you can see, but for now I'll not talk about them. I'll only focus on these three. So just to give some examples of these things that are simple and NSOP1 but not stable. So a simple non-stable theory would be the random graph. So that's the theory where we have an infinite graph, and for any two disjoint finite sets of vertices, there is a vertex that's connected to everything in the first set, but to nothing in the second, or has an edge to everything in the first set, but to nothing in the second set. So this is, in a sense, this is like an infinite set where we randomly add edges, and it's also where it gets its name from. And it's really like just an infinite set would be a very stable theory, and this noise that we get from these edges is what makes it unstable, but apparently still simple. And there's, of course, also an example of NSOP1 non-simple theory, for example, the infinite dimensional vector spaces with a bilinear form over an algebraically closed field. So this is non-simple and is also non-stable. So these inclusions are proper in the sense that, we have examples that they do not reverse. Another example of such a thing, something that's NSOP1 non-simple, was presented by my supervisor, Jonathan Kirby, in this seminar a few weeks ago. So by work by him and Levon Haikasyan, existentially closed exponential fields are NSOP1 and non-simple. But these things do not fit in this framework of first order logic. You have to go to a more general framework of positive logic. And that's kind of the goal of this talk in a nutshell. Can we still make sense of this, this classification picture in more and more general settings? And well, spoiler alert, the answer will be yes, and in very general setting, which I will talk about in the second section. So we have these very concrete examples, and I want to give you an idea of what these classifications, their definition looks like, well, classically. So I don't expect you to right away understand this definition. Actually, I expect you to not understand it right away, but that's not the point. I just want to give a feeling for the kind of definition that's involved. So really quickly, this will be the definition of a simple theory. So formula is said to have the tree property if there is some tree of parameters in some model, some integer, such that every branch in the tree is consistent. And for every level in the tree, it's what we call K inconsistent. Yeah, so this is a very combinatorial picture. I don't want to spend too much time on it. And the point then is that we say that a theory is simple if no formula has the tree property. So this is, I mean, this is a solid definition, but it's very hard to check if you are simple, because to prove that a theory is simple, I have to verify that for every possible formula, no such tree can exist. And that can be quite a lot of work or hard to do. And this is where independence relations enter the picture, because as we will see, we can use them to, well, give these classifications as well. So what's an independence relation? Well, let's take vector spaces as an example. So we have a vector space V and ABC subsets of V. Then we say that A is independent from B over C, and we write it in this anchor notation. If the span of A and C intersected with the span of B and C is contained in the span of C. So you should really read this notation in general as all the information that B has about A is already contained in C. And what we call this an independence relation, and I mean, the reason for the name may already be obvious from this definition. It really uses linear independence. It generalizes the idea of linear independence. And for example, in algebraically closed fields, it would generalize algebraic independence. So the name is really fitting. This is the definition again, and then this independence relation has a bunch of very nice properties. For example, it's symmetric. We can swap the ears of the independence relation, and this should be direct from the definition, right? It's also monotonic. So if B prime is contained in B and A is independent from B, then A is also independent from B prime. Again, should be obvious from the definition. And then there are some more, and I'll go into them later. But for now, let's, just to give an idea of the kind of properties that I'm talking about. And then I promised that we can use those to classify these theories. And this is what we do by what we usually call Kim-Pillay style theorem. So we can classify theories by the existence of a nice enough independence relation. Well, there's this theorem of Kim and Pillay in 1997. A first order theory T is simple if and only if there is an independence relation that satisfies a certain list of properties. And in this case, it's given by dividing. So this theorem says roughly two things. We can use these independence relations to place theories in this classification picture. And such an independence relation is canonical in the sense that there can be only one such independence relation. Because any two such independence relations, they have to both be given by dividing and thus must be the same. Now, I have not told you what dividing precisely is. It's again, maybe a bit combinatorial definition. It's not very enlightening, I think, but it's just a way of giving an abstract definition of an independence relation in just any theory. And in simple theories, it is thus particularly well behaved. Yeah, so the independence relation that I just showed you for vector spaces, that will tell us that vector spaces are indeed simple. Of course, vector spaces are stable, as I mentioned before, and similar theorems exist for stable theories by, actually, this was proved way earlier by Arnick Harrington, Oscar and Shelach, or combined work of these people. So, we can also use that independence relation for vector spaces that I just showed you to conclude that it's even stable. And very recent work by Chernikov, Kaplan, Kim, and Ramsey, we get a similar theorem for NSOP1 theories. So these three classes that I'm interested in, stable, simple, and NSOP1, we can use these independence relations to classify theories. Where they should be in that picture. So now the goal kind of will be to do this, but then category theoretically, and for that we need a framework to work. And this will be the framework of what I call abstract elementary categories. So since we're kind of taking inspiration from this world of model theory, where we work in the category of models of first order theory, it would be natural to ask what nice properties does such a category have. So I write mod T for the category of models of T and elementary embeddings as arrows. What nice properties do we have? It's an accessible category. It has directed colimits. All arrows are monomorphisms because elementary embeddings are always injective. So, and it has the amalgamation property. And that means the following, that any span of arrows, so say A to B and A to C, can be completed into a commuting square. And actually, these are all the properties that I will need. So kind of you could take this as a definition of an AE cat or abstract elementary category. But I want to do something a bit more because sometimes it will be interesting to actually be able to work with subsets of models. And in a category of models, we just don't have quite access to these things. So to remedy that, I'll define this category submod T for the subsets of models of T. So it looks as follows. The objects are pairs AM, where M is a model of T and A is a subset of M. And then an arrow from AM to Bn is an elementary embedding from A to B. So that means that it is a function from A to B, such that for every formula and every tuple in A, we have that M satisfies phi of A if and only if N satisfies phi of F of A. And then obviously this category of models can be considered as a full subcategory of category of subsets of models via the obvious embedding that sends a model to the full subset of itself. If we want to work in a category of subsets of models, we still need to keep track of which objects are considered to be models. This is important model theoretic information. And that inspires the definition of an AE cat or abstract elementary category. We take a pair, CM, which are both accessible categories, and M is a full subcategory of C, such that M has directed colimits, and these are preserved by the inclusion functor. And all arrows in C and thus also in M are monomorphisms. And we call these objects in M the models. So you should really think of C as just, for example, this category of subsets of models or whatever, and then M as just a category of models in there. And then we say that this pair has the amalgamation property if M has the amalgamation property. So actually, almost all conditions are just on M here. And in particular, if I have any AE cat CM, then MM will also be an AE cat. So we can always restrict to just looking at the models and just work in essentially a single category. It's just that C is there to make the framework flexible enough so that we can also work with subsets of models. A bunch of examples of these things. Of course, the kind of motivating example should be an actual example. So for first order theory T, both submod T and mod T, and just only the models of T are AE cats with the amalgamation property. Actually, for positive theory T, we get a similar construction. So this is in the sense of positive logic that Jonathan talked about a few weeks ago. And we take the models to be the existentially closed models and immersions as arrows. And we can define subsets of models very similar to what I did a few slides ago. And then we get, that these things are again AE cats with AP. And I use the same notation because this is really just a generalization of what happens in the first point, right? Because any first order theory T can be considered as a positive theory, and then everything specializes to the original notion.
Mark, what's immersion? What's immersion?
Sorry?
What's immersion?
Immersion, that is, let me just quickly go here. That's if I, for this function, if I restrict to positive existential formulas, and then require that this if and only if statement. So it's sometimes also called embedding, I think, but embedding is then also used for embedding of L structures. So I find that confusing terminology, so I prefer this one. Yeah, right. So we can also find nice examples in continuous logic. So for continuous theory T, we can form the category of metric models. And again, in a very similar sense as we did before, subsets of metric models where we only consider closed subsets. And then these things are then AE cats with AP. And John already mentioned them when introducing this talk, abstract elementary classes. They are also AE cats. So an abstract elementary class K, it is an AE cat itself, if you consider it as a category, or again, with a similar kind of construction where you have access to the subsets. Now, AECs don't generally have AP, but of course the AE cat has AP precisely when the AEC has AP. But AE cats are more general because the things in this third point, so the continuous logic, it doesn't fit in the framework of AECs. So they're, yeah, it shows that these AE cats are more general. All right, so these are examples. And maybe try this talk if you want to keep a concrete example in mind. I think that this one, subsets of models and models, is the best one to think about. Now, we want to do model theory in this framework. And model theory, and definitely classification theory, is all about types. And these are not types in the type theoretic sense. These are sets of formulas. So what is in a first order theory a type? Well, consider a tuple in some model, and then the type of that tuple, which we write as this, is all those formulas that are satisfied by that tuple. And we would like to make sense of this in this setting of AE cats, which seems to maybe be very hard at the first glance because, you know, we have no syntax in AE cats. We don't have necessarily access to tuples of, you know, whatever. But luckily there is this proposition, which is really an exercise in any model theory book. Anyway, so if I have two different tuples, say A in M and A prime in M prime, and they have matching lengths, then they have the same type precisely when there are elementary embeddings into some bigger model N, such that f of A is G of A prime. And I like pictures, so here's a picture of that proposition. We have that they have the same type, if and only if there is a commuting diagram like this. So here I view the tuple A as just a function from some index set X bar to my model, and the same for A prime. And of course, saying that f and G, or that f of A is G of A prime, is the same thing as saying this thing should commute. And this is something that, a picture that should be more appealing to category theorists, I think, because it's a diagram. And this then inspires the definition of what we call Galat types. I should say Galat types are not a new idea. They are already used a lot in this AEC world, but there they are still phrased in terms of elements. But then, you know, to make sense of them category theoretically, we just replace elements by arrows and be happy. So let me give a precise definition. We start with an AE cat with AP. And then I have the following notation to mean that these AI are arrows into M, and that M is a model. And then I say that two such tuples of arrows have the same Galat type, and we write that as you can see here. If for every I their domain is the same, domains need to match if we want to say anything about amalgamation at all. And there are common extensions from M and M prime to N, such that the following commutes for all I, well, same diagram as we had before. So from this point of view, types or Galat types really become a statement about being able to amalgamate things or not. And it should be clear from the definition that having the same Galat type is symmetric and reflexive. And by assuming the amalgamation property, it's also transitive. That should be really a back of the envelope kind of argument. So a Galat type as an object is just an equivalence class of arrows. And when we think back to the kind of syntactic types that I showed you before, like in the first order theory, then Galat types really correspond to this syntactic notion of types. in the sense that they induce the same equivalence class. Right? They're not literally the same because one is a set of formulas and the other is a collection of arrows. But in the end, it's really this equivalence relation that's important, and that thing is the same. And this is also true if we take an AE cat from positive logic or continuous logic, where we have similar notions of syntactic types, but for positive formulas or continuous formulas or whatever. And then again, we can prove a similar kind of amalgamation proposition, and we see that these things coincide again. Right. So now we have made sense of some basic model theoretic stuff and the framework. We can start talking about these independence relations and see if we can kind of recover a bit of this classification theory. And here I really want to mention the work by Mike Hirschi and Sebastian, because it was a big inspiration for this project. I'm sure they have talked, or someone of them has given a talk about this in this seminar. Anyway, to briefly recap is they view an independence relation on an accessible category as just a collection of commuting squares. And if you think about the category of models of a certain theory, then such a commuting square, you can just view these M0, M1, and M2 naturally as subsets of N. And then they say, you know, this square is independent if we would write it model theoretically like that. So this square is independent if M1 is independent from M2 over M0. And then they prove, among other things, that they have canonicity of stable-like independence relations. So they identify a bunch of these properties, which they phrase in this category theoretic language. And then these are really the properties that you would expect to hold in a stable theory. And then they prove canonicity. And what I want to do is take this idea and then also do the same thing for simple and NSOP1-like independence relations. For me, an independence relation will be a slightly different definition. So work in an ECAT with AP. And then for me, an independence relation is just a relation on triples of subobjects of models. So if you have a triple ABC, which are subobjects of a model M, and if that triple is in the relation, we say that it is independent and we write it as with this notation that we have seen before. And really, this is ultimately not so different. In fact, if you have an AECAT of the form MM, so there's really only one category that we're talking about, and this is really essentially the same as this commuting squares notion. And you can make this precise in the sense that modulo some basic properties, you can recover one from the other. So it's really the same information, it's just a different way of presenting it. The advantage to this, to presenting it like this, is that you get a more intuitive independence calculus. So the properties are a bit more intuitive to phrase and to work with, because you don't need to make everything a commuting square. You have a bit more freedom what you put on the sides. The disadvantage, though, is that in their work, Mike Hirschi and Sebastian, they have this very nice way of viewing an independence relation itself as a category, right? Where you take the category of arrows and then the morphisms, those commuting squares that are considered to be independent, and then they do all sorts of nice things with that viewpoint. So, well, every disadvantage or every advantage comes with a disadvantage, but in the end, it's the same information anyway, so you could recover this from one and one. And then I promised to give a bit more, or to actually make precise what this list of properties is that I talked about at the start. So I'll show them now, but in the language of AECATs. So I'll call an independence relation a basic independence relation if it satisfies the properties that are about to appear on the screen. And the reason for this is that I really want any independence relation that I consider to at least satisfy this. So we have invariance. So it's invariant under having the same Galat type. And that means that if A is independent from B over C, and ABC has the same Galat type as A prime, B prime, C prime, then A prime is also independent from B prime over C prime. Monotonicity, so we have seen this one before, although I think I did it on the other side, but whatever. So A is independent from B, and A prime is below A. then A prime is independent from B. There is transitivity, so I have not talked about this one before. This is given two independence relations, like A independent from C over B, and A independent from D over C, and B sits inside of C, and I can kind of stack the right sides on top of each other, and then I get A independent from D over B. Symmetry, so I can swap the ears again. So this also means that, it doesn't really matter if I phrase, for example, monotonicity on the left or the right side. I always want symmetry. Existence, A should always be independent from C over C for any A and C. And this is the first one that's a bit more complicated, extension. So if I start with a triple ABC arrows into M, and I have A independent from B over C, so these are the subobjects that are represented by these arrows A, B, and C. And I have some B prime extending B, then I can actually find an extension, by which I mean just an arrow from M into a bigger model M prime, and some A prime in that M prime. So you said A prime BC has the same Galat type as ABC, and A prime is actually independent from this B prime. So what this says is that you can extend one side of your independence, but at the cost of finding an isomorphic copy on the other side. And I should say something about the notation here. So for example, here I suddenly consider B as an arrow into M prime, but that's really by saying, well, B is an arrow into M, and then I compose it with this nameless extension. And this is the last one, union. So if I have a directed system, and suppose that the colimit of that directed system exists, and if I'm independent from everything in that system, I'm independent from the colimit. So in particular, if this directed system consists of models, then the colimit will always exist. And this applies. I should say here that this is a stronger assumption than Mike Yoshi and Sebastian usually need in their work. This really corresponds to what we in model theory call finite character, or in AEC land, we call this often the Aleph not witness property. But yeah, for the kind of stuff that I want to do with this union axiom is really, really necessary. Okay, so this is what we call basic independence relation. And then there are a few more advanced properties. And the reason I call them advanced properties is because they are exactly the ones that determine where in this classification picture we will land. So the first one is really simple. It's base monotonicity. It's A is independent from B over C, and C prime is in between C and B. Then I can kind of increase the base, and A is independent from B over C prime. There's club local character, for which I will not give a precise definition, but because it's a bit technical. But the idea is that for any A and any model M, which are subobjects of N, there are many small, so many and small are very imprecise here, but there are many small M0 submodel of M, such that A is independent from M over M0. This may seem a bit like weird kind of thing to require, but if you think back to this vector spaces example, and say A is a finite linear subspace, right? And M is just a very big model. Then A will be independent over the intersection of A and M from M by how we define this linear independence. But this intersection of A and M will in particular be contained in A and will then be a finite dimensional linear subspace. So that's however big M gets, A will always be independent from M over a finite dimensional thing. And this is really what small means. So that's phrased in terms of presentability, but it just says that, M can never contain too much information about A. And many here refers to there is actually a club set of these M nodes, if you know what that is. Okay, and the next property is stationarity. So it says that if A and A prime have the same type over M, and they're also independent from B over M, both of them from B, then already A BM and A prime BM have the same type. So this in a way says that there is only a unique extension to an independent type. And for that reason, it's sometimes also called uniqueness. I think in Mike Hirsch's and Sebastian's work, they call this property actually uniqueness, but this is really the same thing. Right. And then there is one more property, and that's tree amalgamation. And I think that's best explained using a picture. And the picture is as follows. So the input data is the solid arrows here. And we want them to be in such a way that these top three independent things hold. But I mean, in words, it's just saying that every one of these three solid faces is an independent, well, square, if you want. And then tree amalgamation says that given that input data, I can find these dashed arrows, these extensions, such that the entire thing commutes, and such that A, which is over here, is independent from N3, which is over there. And note that N3 in particular contains B and C. So in more classical formulations, you would say A is independent from B and C, but we don't necessarily have unions in our category. So I need something containing that. So that's really what tree amalgamation is. And now that we have all these properties, we can finally start to try to rebuild this classification picture. And to do that, we start with a basic independence relation. And we say that this thing is NSOP1-like if it satisfies club local character and tree amalgamation. So it's a basic independence relation that also satisfies these two advanced properties. If it then in addition also satisfies base monotonicity, it's called simple. And if it in addition to that also satisfies stationarity, we call it stable. And so you see that this is really an increasing definition, right? So anything that's stable is simple, and anything that's simple is NSOP1-like, just as we had in the picture at the beginning. Now, this is not the most economic definition possible. For example, in a stable independence relation, tree amalgamation will already follow from stationarity modulo some of these basic properties. So if you actually want to, find out whether or not your relation is stable, you don't need to check that property. But just to make it, to really emphasize this increasing definition, this hierarchy that we have, I like to keep them in there. Right, so we have these notions of independence relations, and then we can state the theorem, the results that we get from them. So if we start with an AE-cat with the amalgamation property, and suppose that we have a simple independence relation, then that thing is actually given by what I call easy dividing. Now, I have not given a definition of easy dividing, and again, it's just as I didn't want to give a definition for dividing, this is even harder and less enlightening. But I mean, the name is not chosen at random, it's really a generalization of that, or more or less. But the point is that this gives us canonicity for simple independence relations, right? Because any two such independence relations have to be given by easy dividing, and thus they must coincide. And well, every stable independence relation is simple, as we, by definition. So the above also implies that we have canonicity for stable independence relations, which of course we already knew by work of Mike Hirsch and Sebastian, and that is more general. But it starts rebuilding this classification picture because now we can compare stable and simple independence relations. And then there is also this theorem. So the previous theorem has been published, so you can look it up if you want to know more precisely what, for example, easy dividing is and how it works. This theorem is still work in progress in the sense that I should write a preprint at some point, but anyway. So again, we have an AE-cat with AP, and we assume the existence axiom, and I'll say in a bit what that more or less means. Then suppose that we have an NSOP1-like independence relation, then that thing is given by long Kim dividing. And this is again one of those notions that I don't want to give a precise definition, but it implies canonicity of NSOP1-like independence relations, just as before. So what is this existence axiom? Well, it's talking about the existence of certain independent sequences. So by assuming the existence axiom, we assume that certain independent sequences exist. And it's really a mild assumption because, for example, it's satisfied whenever we have a simple independence relation. So if we are in the setting of the first theorem, then it's always satisfied. But it's also satisfied in many of these examples that we considered. So if we work over models, for example, over first order theory, so an AE-cat of the form of this form, then it's always satisfied. The same is true for models of a continuous theory, and even in a certain to a certain extent for models of positive theory. But we do need, in general, this assumption because if we want to work over, even if we want to work over arbitrary subsets in something as nice as a first order theory, then it's not known whether or not this thing always holds. And to be more precise, it's an open question whether in a first order theory that has NSOP1, so it's relatively nice, whether or not existence is always true there. For as far as we've been able to verify manually, this is true, but in general, it's still needed as an assumption. So if we need it in a very nice first order case, we will definitely need it as an assumption here. Okay, so these are the theorems, and then these theorems really allow us to rebuild part of this classification picture that I showed you at the start, based on independence relations. Because clearly we have stable implies simple implies NSOP1, but this canonicity is really useful if you want to characterize or classify where in that picture you belong. And let me give an example of that. Suppose that you have an NSOP1-like independence relation, but suppose that it fails base monotonicity. So remember, this was one of those properties that, this is the distinguishing property between NSOP1-like and simple, right? So it's NSOP1-like, but it fails base monotonicity. Then this AE-cat can never have a simple independence relation. And that follows from these theorems, because suppose that there would be a simple independence relation, then that would mean that we have the existence axiom. So the second theorem from the previous slide applies. And then by canonicity, these two independence relations have to be the same, but that cannot happen because a simple independence relation always satisfies base monotonicity. And this is really a way to very precisely place, well, AE-cats, I guess, in this classification picture based on the existence of independence relations. Yeah, and that's where I want to stop. So if there are, so these are the references that I mentioned throughout. If there are questions, then I'll be more than happy to answer them. And thank you for your attention.
Muted. So thanks very much for a nice talk, Mark. If anyone has any comments or questions, go ahead.
Yes, that was very nice. I would like to ask you, you defined types using morphisms instead of elements. Can you get stability using those extended types or not?
Stability in the types counting way, you mean?
Yes, so it's valid for those morphisms types or not?
I have not precisely verified this, but I think it should, the kind of standard argument should go through. Yeah. Okay. Yeah. I think I want to say yes, but I don't know for sure. I know for sure that if you are simple non-stable, then you get too many types by kind of the standard construction that you can find a very big kind of branching tree of different types. But I don't know if the other direction is true. So if given a stable independence relation, you always get few types.
Yes, because the advantage is that you don't need underlying sets for your types. Yes.
Yes. So I imagine that, because I think that's something that you prove in your paper, right? But then for the underlying, for actually element-based types. I would think that, those proofs should kind of almost go through whenever you replace element by morphism. Because this is more like in my experience when trying to do these proofs, that it's almost whenever something works in an AEC, say, then you replace element by morphism and maybe be a bit creative here and there. But yeah.
Mm-hmm. Yes, yes.
But it is an interesting question.
Could I ask? So maybe I'm remembering something from a draft ages and ages ago, but I had the feeling that there was a strong kind of analog of tameness at play that was helping this calculus work. And I don't know if I saw that in the talk today.
No, you're exactly right. That was in an early draft of the first theorem. So this theorem.
Yeah.
But I've been able to remove that assumption. So I had an assumption about type shortness. So Aleph not type shortness. So that, a type is determined by the finite subtuples. But that's no longer necessary. And that's really, I really needed that to kind of make sense of indiscernible sequences.
Mm-hmm.
But then I kind of completely moved away from using indiscernible sequences because they only make sense in a type short, in an Aleph not type short setting. And that's kind of where this EC dividing was born, because it's dividing with respect to what I call EC sequences rather than indiscernible sequences. These EC sequences are still somewhat homogeneous, but by far not as much as the indiscernible sequences, just enough to do this proof. I hope that at least makes some kind of sense, although it's a bit handy.
It does. Thanks.
Any more comments or questions? Go ahead. Yeah.
Yeah, maybe just a very non-technical question. Namely, so when you defined AE cats, that was a tuple of accessible categories where M is contained in C, basically, right?
Yes. Yes.
And then you continue to give a bunch of definitions and a bunch of structure, which always was talking about models, where models are elements in M, right? Or more.
Right. These things you mean? Or
and these are the examples, right?
Yes.
That you had in mind. And then you continued defining independence relations and stuff. Right, which seemed to be basically about things in M, right?
Well, yeah. So okay. So here,
So the question is basically where do these notions really depend on C? Where do you?
Right. So here, maybe I didn't say that clear enough. So these ABC are sub-objects, but they live in this bigger category C, so they can be any subset, if you will.
Okay.
I just require the top to be a model.
Okay.
So the depth.
Okay.
So this is where this bigger thing comes in. But as I said before, it's often you can just actually look at the category of models, and in fact, all this information about where in the classification picture you belong, it's always contained in the category of models. So this kind of flexibility is really for other reasons than that.
Mm-hmm. And can you just give me some? So I'm for somebody not working in model theory. So your main example was the category of subsets of models over some theory, right? Why do we look at that, and why do we look at such relations on just general subsets?
Okay, so to give just one very concrete example that goes in the kind of same motivation as this entire story, let me go to this property that I called club local character. Here I say I want a small M node. And I actually say it needs to be a model. If I replace that by, I actually want a finite subset. So, I guess that in a category you would have to say finitely presentable or whatever, but finite subset. Then if I go to the classification picture, there is this dividing line as well between super stable, super simple, and actually stable and simple. So it kind of cuts this simple and stable in half. And the difference between them is that this thing that we get in the base is actually so small that it is finite. While outside of that, it can be infinite, but still relatively small. So, but since all your models will be infinite, you really need information about subsets there to distinguish between those two.
Mm-hmm.
So I have not really made this precise in my work, but that could be for a future direction, could be an interesting distinction to make.
Okay.
I hope that makes some sense.
Yeah, thanks.
Thank you.
Any further comments or questions?
I can give another answer to the last question if it
Oh,
helps.
yes, please, yes. You probably know more about that than me.
Well, there's just another example. So one of the basic examples that model theorists use for everything is the theory of algebraically closed fields. So a model is an algebraically closed field, but the subsets of those, I mean, interesting subsets are fields, right? So there are fields which are interesting, which are not algebraically closed. And so it's nice to know about independence of fields, not just algebraically closed ones. And be able to, and even just be able to say what it means for two fields, two field extensions of something, or two subfields of a big field to be independent over some common subfield. So it's useful to be able to say what that means, even if it doesn't tell you more about the stability class of the whole theory. It's something that you might want to talk about.
Thanks. That's indeed also a very nice example.
Yeah, thanks.
May I ask it? There's this notion of finite character for the abstract elementary classes. Do you have anything like that here in this more general setting?
Do I have anything like that? What's the question?
Like finite character, yeah. Which is
yeah, that's my union axiom. I don't know if it's literally the same thing. Probably this is maybe technically a bit weaker, but
okay.
But this follows directly from union, from finite character kind of things. Right?
Okay, I see. So this is stronger than that, okay, or weaker?
I think if anything, it's weaker.
Weaker. Mm-hmm.
Because finite character always implies this, right? Mm-hmm. Because if I have
collimate of finite things, yeah, okay.
Yeah. So a directed system is just you could replace this by chains if you want.
Mm-hmm.
It's equivalent.
Okay, I see. Mm-hmm.
Maybe then a follow-up question to the explanations you gave to my former question. So does anything change if we basically layer what you do by, instead of looking at a theory T and then at all subsets of their models, but at looking at a sub-theory T prime and then looking at models of T prime, which are not models of T, or, you know, something like that. So instead of looking at all subsets, we look at models which are, models of that sub-theory, and then do the same game. So you have then for example, you have the algebraically closed fields, and then you have the theory of just all fields.
Yeah. So I think I can't really give a precise general answer, but well, maybe to some extent, because it is an interesting question. And yeah, so if I think about this positive logic, then we have these existentially closed models, which are kind of, these are considered to be this M in this category. But there's also just models. So there are models that are not necessarily existentially closed. And fields and algebraically closed fields are an example of this. So I can take the positive theory of fields, then models are just fields, and the existentially closed models will precisely be the algebraically closed models. And then you get an AE cat again, where this is not submod T, but just the non-existentially closed models. And then we pick out the existentially closed models. And then you could try, you could ask about these independence relations again. At least the entire framework applies, but I have not, thought about what particular examples there might precisely mean, or what information you get from that. So you can phrase the question even very precisely in that sense, but I don't know if it has any answers or any interesting answers. or what information you get about it.
You can go in the opposite direction too. You can take models as your C, and you can take models with extra properties like saturation properties as your M. And this is actually quite common in Chelas' work, that he doesn't work with all models. He has to work with these omega saturated models, or Aleph, which it is Aleph 1 saturated models, and there's some Aleph epsilon saturated models, which is slightly stronger condition than Aleph naught saturated and slightly weaker than Aleph 1 saturated. And there's things called A models. And there's all these sort of slightly saturated models that if you work with those, you get nicer properties and you can do things. Or you could even work with very saturated models. So there's that sort of thing where you definitely it's nice to have that flexibility.
Yeah, definitely. Actually, maybe this is an answer that's really geared towards you then, Jonathan, but this is happening kind of in the work that I am doing with Jan on NSOP1 in positive logic, where we need these things to be kind of lambda T saturated, right? Because we want to make sense of Laskar-strong types. And now lambda T saturated, saturation for something bigger than Aleph naught will generally not work, because then you lose directed co-limits in this category. But you can kind of get it back by some trick, which I don't want to get into the details right now. But yeah, so it is, as Jonathan said, sometimes the other way is also important, that you can actually look at an even stricter subclass of models, which has even nicer properties. And yeah, it does that as well.
Any more? Anyone got another question or comment? Well, if not, then let's thank Mark again. Very interesting talk.
Thanks for all the questions.
Yeah. And okay, well, so that's it for today. So we can